The following lecture will cover acids and bases in organic molecules, with a particular focus on the structural features that affect acidity and basicity. 3.1 begins with a review of Bronsted-Lowry acids and bases, which hopefully much of this is familiar from Chem 1. If not, I'll quickly go over the important features of the acid-base theory that you need. Okay, so we begin by defining acid-base reaction as a proton transfer reaction. So when I say proton, I'm talking about an H+. Think about a hydrogen atom has one proton and one electron. If you remove an electron, you're left with H+. And that essentially is just a proton. That's why we call it a proton transfer. So this proton, H+, gets moved from acids to bases. The conjugate acid-base theory that you learned in Chem 1 simply states that a conjugate acid results when a base accepts a proton, and a conjugate base results when an acid gives up a proton. So the first skill is being able to identify acids and bases, right? And then we can identify their conjugates. So an acid is a proton donor, and a base is a proton acceptor. So acid, Bronsted-Lowry acid, is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So given a proton transfer reaction, let's identify the acids, bases, and their conjugates. All right, so if you look at the first molecule, HCl, look what happens to it. HCl has lost an H+. The electron has gone to the chlorine atom and become chloride. So HCl has donated a proton, therefore it's the acid. If you look at water, water has accepted an H+. Therefore it's the base. It accepted a proton, so it's the base. And to identify the conjugates, you say every acid has its conjugate base, and every base has its conjugate acid. A conjugate acid-base pair only differ by an H+. HCl and Cl- differ only by an H+. H2O and H3O+, this is the hydronium ion, differ only by an H+. Here we have another example of a problem where we want to label the acid, base, and their conjugates given the structures. So if we look at our first molecule, let's look what happens to it. It has gained a proton. That makes it the base. And if we look at water, water has lost a proton. That makes it an acid. So every base has its conjugate acid, and every acid has its conjugate base. In the last example, water was behaving like a base. And in this example, water is behaving like an acid. Water is amphoteric, meaning it can act as an acid or a base. The next section deals with the curved arrow notation, or the mechanism for acid-base reactions. There always the same. It's extremely important that you learn how to draw these two arrows correctly. So we're going to go through each of the steps. A reaction mechanism simply shows the curved arrows, which represent the movement of electron pairs, very similar to the resonance arrows that we were drawing. However, this is different because we're making and breaking bonds. All right, so the general mechanism for all acid-base reactions. It's a little counterintuitive, but let me tell you the mistake that students make right off the bat. Instead of showing the flow of electrons, students want to draw where the hydrogen goes. So students will draw the hydrogen going to the base. The arrow does not show where the hydrogen goes. Do not draw the arrow with the tail starting on the hydrogen. The tail of the arrow always starts where the electrons currently are, because we have a base that has a lone pair of electrons. They're going to be used to make a new bond with the hydrogen. Just look what happens to that structure in the products. It has gained a proton. Well, how does it do that? Because essentially the base attacks that proton. Now we have to get rid of the electrons. Look at the A here. It ends up with a lone pair of electrons and a negative charge. So the electrons have to leave the hydrogen A bond, that's your acid, and end up on the A. So here's your base. A is your acid. This is your conjugate acid, and A minus is your conjugate base. There's always two arrows. One in which the base attacks the hydrogen, and the second represents the bond breaking between H and the rest of the acid molecule. Every single time. 1, 2. In every single acid-base reaction. They're all the same. So if you learn this basic pattern, you'll be all right. All right. So let's quickly go over how to draw a proton transfer mechanism. First, you need to identify the acid and the base. If you're not sure what your base is, you're not going to know where to start the tail of the arrow. Next, draw the first curved arrow. This is your first one. The tail of the curved arrow is placed on the lone pair of the base, and the head of the arrow is placed on the proton of the acid, which results in a new bond being formed. The second arrow should start with the tail on the HX bond. We're calling A X in this case, okay, in which the bond is being broken. And the electrons are going to end up on that atom. So the tail of the arrow starts on the bond and goes to the atom. And notice how when those electrons go on the atom, it incurs a negative formal charge. Let's look at another example. If we wanted to draw the mechanism draw the mechanism of the proton transfer reaction. Okay, we go through the steps. Let's label the acid and the base. All right, well, this is the OH minus is your base because it ends up getting a proton. And this is acetic acid, but this is the acid because it the oxygen ends up donating or losing a proton. Okay, so once we know the acid and the base, the tail of the arrow starts on the lone pair of the base every time, and it ends up on the hydrogen. First arrow. Second arrow always starts on the bond between the hydrogen and the rest of the atom connected to the rest of the acid. Okay, and then we dump those electrons onto the atom. Every time, it's always the same. We'd say the base attacks the acid. We have our two arrows representing the two pairs of electrons that are moving. Here's the first pair that end up forming a bond with hydrogen. And that second pair of electrons were in that bond, and they end up here. In the next two examples, you should stop the video and give these a try on your own. In the first one, try to identify the proton transfer steps that are occurring by looking at the arrows and matching what you know about the acid-base mechanism to what you're looking at. And for the second one, actually try to draw the mechanism for each of these reactions. All right, hopefully you got a chance to try these. Let's take a look at our first example. All right, in the first one we see two sets of arrows in which the first arrow starts on the tail, or the tail of the arrow starts on a lone pair of electrons and the head goes to a hydrogen. And in the second, it looks like the tail of the arrow starts in a bond and it ends on an atom. So this is, that's a 2. This is our acid-base proton transfer mechanism. So this is a proton transfer. Our second step is not a proton transfer. That's actually called loss of a leaving group, but we'll get to that in chapter 6. And step 3, it looks like the tail of the arrow starts in a lone pair, goes to a hydrogen, electrons from a bond end up on another bond. Now, they didn't end up on an atom. The only thing different here is in our other proton transfer reactions, the head of the arrow ended up on an atom. Now, technically, you could have done that and taken a pit stop with a carbon with a negative charge, and then with our resonance structures or resonance patterns, you would have had a lone pair adjacent to a positive charge. So this basically combines both of those steps. So it doesn't violate our proton transfer mechanism rules. It just incorporated a resonance step in it. So this is also a proton transfer. All right, for the next example, we need to identify the acid and the base and then draw the arrows. So it looks like the CH3O- is going to be the base, and water is going to be the acid. All right, and the tail of the arrow starts in the lone pair, goes to the hydrogen, and then our second arrow goes from the bond to the atom, and that's our proton transfer mechanism. In the bottom example, we have the nitrogen-containing compounds. This is dimethylamine is our base, and water is the acid. So the tail, and this is a neutral base. So we have that, and we get our products. In the next section, we're going to talk about quantifying acidity and basicity. We're going to be comparing different structures and trying to determine which is more acidic or basic. So the qualitative approach is where we look at the general stability of the structures, and the quantitative is where we're going to use pKa's to assess acidity. So we're going to be using pKa values to assess acidity. And if you haven't done so already, make sure you have a pKa table printed out. There's one in the back of the notes. You absolutely need it for this section. All right, so let's talk about what pKa is and where it comes from. In Chem 1, you did equilibria, and then you talked about acid-base equilibria. Double arrow means equilibrium. All right, so we can write a Ka, that's your acid dissociation constant, and its products over reactants. Water is not included because its phase label is a liquid. These are all AQ. If you remember, you never include liquids or solids in your equilibrium expression. So water does not get included. All right, and if you take the negative log of your Ka, then you get the pKa. So what does that mean in terms of acidity? Well, hopefully, maybe you remember that the greater the Ka value, the stronger the acid. Why? Because we have a greater percentage of dissociation or greater percent ionization of that acid. That means that the equilibria lies further to the right, the larger Ka is. So the relationship with Ka and pKa is inverse. The larger the Ka, the lower the pKa, because the pK is a logarithmic function. So, in a nutshell, the stronger the acid, the lower the pKa. The weaker the acid, the higher the pKa. Now, each pKa unit represents an order of magnitude or a power of 10. So let's take a look. Sulfuric acid has a pKa of -9. HCl has a pKa of -7. H2SO4 is 100 times stronger than HCl. So if you wanted to calculate this, you would just take the difference here is 2, -9 and -7. That's 2. Take the absolute value, right? You can even just do 9 minus 7 equals 2, and that is 2 orders of magnitude, so you just put it as 10 to the second, and 10 to the second is 100. So that tells us that based on the difference in the pKa, it's 2 orders of magnitude difference, and that translates to 100 times stronger of an acid for H2SO4. All right, you're going to need the pKa table that's in the end of the notes now. Make sure you have this in front of you for the rest of the section, or else you're not going to understand what we're talking about here. So the first skill is you need to be able to use that pKa table and assess relative acidity. That means compare 2 acids and determine which one is more acidic. So look at your pKa table. I want you to find acetic acid. Don't look in the right-hand column in the conjugate bases. Just look in the left-hand column with the acids. That's all you're focusing on here. So find acetic acid and then find this structure. It happens to be acetone. And the acidic protons are the ones that are in red here. So acetic acid has a pKa of 4.75. Acetone, that proton there, has a pKa of 19.2. Remember, the lower the pKa, the stronger the acid. So, acetic acid is more acidic because it has a lower pKa. All right, next, I'd like you to give this a try. Pause the video. Use the pKa table to identify the pKa values for each of the compounds for each pair and to determine which is more acidic. When you come back, I'll show you the answers. All right, hopefully you were able to give this a shot. Let's take a look. Our first compound, it's at the very bottom of the pKa table. The pKa is 50. And the next compound that also has a pKa at the bottom of the table, the pKa value listed for this is 25. So the lower the pKa, the more acidic. So that's our more acidic compound. All right, for our next one, we have 4.75, and water was 15.7. So this happens to be the more acidic compound. The next one, pKa is 9.9, water was 15.7, more acidic compound. Hydronium is negative 1.74, and HCl was negative 7. So that is a lower pKa. HCl is more acidic. All right, so oftentimes you won't always find the exact structure on the pKa table. However, you need to be able to look for a functional group with a similar molecular arrangement so you can assess acidity. So this is the first place where functional groups are absolutely critical to know. All right, so we're going to still use that table 3.1, which is the pKa table. All right, however, what I want you to do is you're going to be looking for the functional groups that I mentioned. All right, so we want to assess the acidity of these two protons. All right, it looks like I've got an alcohol, a COH, and that happens to be a secondary alcohol. Well, a primary alcohol, so the primary alcohol was 16, and the tertiary alcohol was 8, had a pKa of 18. So because this one's secondary, let's just say it's somewhere in the middle. All right, so we have a pKa of approximately 17. All right, for the next one, well, we have a hydrogen attached to a nitrogen. On the bottom left of your pKa table, you have NH3. And that had a pKa of 38. So this is approximately 38. So since the alcohol has a proton with a lower pKa, we say that this is the more acidic proton. All right, so I'd like you to give this one a try on your own. Pause the video, use the pKa table, and try to identify the pKa's and then rank them according. All right, hopefully you're able to give this a shot. All right, let's take a look. Our first proton, HA. Well, that looks like we have an aromatic ring with an alcohol. That's actually called a phenolic ring. However, this has a pKa of approximately 9.9. Our amine, HB, had a pKa of 38, roughly 38. And HC, if you look a little bit further up on the pKa table, we can say that this is similar to acid or acetic acid, right? So that had a pKa of roughly 4.75. All right, so HC is the most acidic. Then we had HA, and then finally HB, because that was 4.75, 9.9, and 38. All right. Moving along, let's take a look at relative basicity. So for bases, it's just the opposite. something is more basic when it has a lower Ka value or a higher pKa. However, the concepts or the ideas that we're going to focus on here are right here. The two ideas we're going to use to solve all of these problems. The stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base. So in order to determine base strength, we're going to be looking at the conjugate acids. You have to do this every time. Then we're going to compare the pKa values, and we're going to identify the stronger base by using these two concepts here. For example, let's identify which of the following is the stronger base. So step 1, draw the conjugates. Step 2, find the structures for the conjugates on the conjugate acids on your pKa table. So our first one has a pKa of 9, and the second one has a pKa of 19.2. Now, if we're looking for the stronger base, that means we're looking for the weaker acid. So, the stronger base has the weaker acid, which has the highest pKa. So when you draw your conjugates, assign the pKa's, look for the highest pKa value of that conjugate acid that you drew, and that structure came from the stronger base. All right, for the next one, I'd like you to try this on your own. So pause the video and give this one a shot. When you come back, I'll show you the answer. All right, hopefully you were able to give this one a try. We want to identify the stronger base, just like that last example. So let's draw our conjugates. These are the conjugate acids of each of the conjugate bases. This is not a chemical reaction here. I'm just using the arrow to show you that we're going from the bases and now we're drawing our conjugates. Now, we're going to identify the pKa values. This is 25 and this is 38. Now remember, we're looking, if we want to find the stronger base, we're looking for the weaker acid. And the weaker acid has the higher pKa value. So this is our weaker acid. And it came from the stronger base. Because the weaker the acid, the stronger the base. All right, so now that we know how to use the pKa table and identify stronger and weaker acids and bases, we're going to analyze equilibria and predict if the equilibria favors the products or the reactants. Equilibria simply means that the rate of the forward and reverse reactions are the same. The amounts of products and reactants does not have to be equal. That is not what the equilibria represents. Equilibria is about the rates of the forward and reaction being the same. So, when we analyze an equilibria, the equilibria will always favor the formation of the weaker acid. All right, so if we want to determine the position of an equilibrium, step 1, we're going to identify the acid on each side, and we're going to compare the pKa values. So, in any given acid-base reaction, find your acid and your base, and now we're going to look for the conjugate acid of our base. This is what we're focusing on. The acid on the left and our acid on the right, or the conjugate acid. We're going to use our pKa table and identify and write down our pKa values, 15.7 and 18. So we're using this concept. The equilibrium favors the formation of the weaker acid. This higher pKa tells us that this is our weaker acid. Therefore, the equilibrium will favor the product side. And we can represent that with just one arrow being slightly larger than the other. All right, so the next type of problem we want to be able to solve is to determine the position of the equilibrium, like we did in the last example, and then determine the factor by which the products or reactants are favored. So, step 1, identify your acid on both sides. Step 2, look up your pKa values. The higher the pKa tells us this is the weaker acid, so the equilibrium favors the products. But now we have to determine by what factor. So to do that, take your pKa values, subtract them. Doesn't have to be products minus reactants or reactants minus products. Just take the bigger one, subtract it from the smaller one, and use an absolute value. So we get 34. The 34 orders of magnitude is the difference. So that 34, remember, like we did earlier in the lecture, just put that right there, 10 to the 34. Oh, 10 to the 34th. So there are 10 to the 34th more products than reactants. That's the factor for which the products favor, or the factor at which the products are favored over the reactants. All right, give this one a shot on your own. When you come back, I'll show you the answer. All right, hopefully you're able to give this one a try. We're going to find the acids on both sides. So here's our acid on the left, and this is our conjugate acid on the right. The hydronium ion has a pKa of negative 1.74, and let's see, that is acetone, that is protonated. Let's find that. That's negative 7.3. So the equilibrium will favor the left. This is your weaker acid. So the equilibrium favors the reactants. Meaning at equilibrium, there's a higher concentration of reactants. And if we want to determine the factor by which the reactants are favored over the products, we just take the absolute value of the difference here, negative 1.74 minus our negative 7.3, and we get 5.56. So we just raise that to the power of 10. That's 5.6 orders of magnitude. So the reactants are favored over the products by a factor of 10 to the 5.6. And you could put that in your calculator, and that's approximately 400,000 times greater. All right, for the next one, let's take a look at the acids on both sides. So here's the acid on the left, and NH3 is the acid on the right. It's your conjugate acid of our base. If we look up our pKa values, this is about 25. And for NH3, our pKa was 38. So this is our weaker acid because it has a higher pKa. Therefore, the equilibrium favors the products. And by what factor? We can take the absolute value of 38 minus 25, and we get 13. So 10 to the 13th is the factor by which the products are favored over the reactants. Or you could say there's 10 to the 13th. A higher concentration of the products is 10 to the 13th greater than the reactants. All right, in our final section, we're going to look at, we're going to move to chapter 25, but this is part of the curriculum. It's been established by the chemistry department here, and we want to look at the effect of pH on the structure of amino acids. So many of you will be going into bio or have taken bio and possibly biochemistry. This will be important. So there are 20 amino acids that are abundantly found in proteins, and the difference between each amino acid is this R group. Right? By the way, we have an amino group, and that's a carboxylic acid. So it's an amino acid. And the only difference between our 20 amino acids is the identity of the R group. So amino acids have that carboxylic acid, which is acidic, and a basic amine, so two functional groups. All right, so each of the highlighted protons has its own unique pKa value. We can call it pKa1 or pKa2, it doesn't really matter. But the pH of the solution containing the amino acids will determine the form that it adopts, meaning will it have a hydrogen or not on each of these groups. So there's two protons that we care about. One on the carboxylic acid and one of them on the amine. So when I say what form it will adopt, I mean, will it take on the cationic form, in which both carboxylic acid and the amine have a hydrogen and the amine gets a positive charge? Will it be the Zwitter ionic form, in which we have a negative charge on the carboxylate ion and then positive charge on the amine? Or will it be the anionic form, in which it's just a negative charge? Zwitter ionic means that the compound has a plus and a minus charge. All right, so before we can get into a particular example, we need to get some vocabulary out of the way. So we need to be able to identify the protonated versus deprotonated form. All right, and when we do that, we're going to consider each functional group separately. Protonated means that the atom has the hydrogen. Deprotonated means that a hydrogen is lost. You need to know this for each of the functional groups. So we're going to talk about the carboxylic acid. That's one end of the amino acid. Then we're going to look at the amino group, the other part of the amino acid. So protonated carboxylic acids have the hydrogen. Protonated amines are going to be NH3. Deprotonated carboxylic acids have an O minus, and deprotonated amines are NH2. So know the difference between protonated and deprotonated. Now, when do we see these? The protonated form of both the amine and the carboxylic acid occur when the pH of the solution is less than the pKa of that proton. The deprotonated form will predominate when the pH of the solution in which the amino acid is in is greater than the pKa of that proton. So you may have to come back to this information until you are really comfortable with protonated and deprotonated forms. It's two functional groups, protonated when they have the hydrogen, deprotonated when one of the hydrogens is gone. All right, so here's how we determine the structure of an amino acid, and you're going to be given the pH and the pKa values. These are given. You won't have to look these up. Step 1, identify the pKa of the carboxylic acid group, and then you compare it to the pH. Determine which form exists. 2, identify the pKa of the amino group. Compare it to the pH. Determine which form predominates. So let's take a look at glycine. The R group is just a hydrogen. So there's 2 hydrogens. That doesn't really matter, but that happens to be glycine. And we're going to look and try to determine what form will predominate in stomach acid, in which the pH is roughly 2. Now I want you to think of the molecule in separate pieces, the amino group and the carboxylic acid group. It looks like I missed half of the sentence there. All right, we're going to focus on the molecule in halves. Let's start with the carboxylic acid. All right. It tells us the pKa of this proton. That's given. Let's compare it to the pH. It's 2. 2 is less than 2.35. When the pH of the solution is less than the pKa, the protonated form predominates. So we draw the molecule with the carboxylic acid having that hydrogen. Let's look at the other half of the molecule, the amine. The pKa is given. Oh, that should be an 8. Typo, I think. One of them's a typo. Anyway. All right, the pH of the solution is less than the pKa of that proton. So, whenever the pH of the solution is less than the pKa, the protonated form exists. Therefore, we draw it as NH3 plus every time. All right, your turn. Here's glycine, same molecule. We're going to determine what form is predominant at a pH of 7.4. So pause the video, give this one a try, and when you come back, I'll show you the answer. All right, hopefully you were able to give this one a shot. All right, so step 1, let's compare the pKa values to the pH values. So in our previous slide, we saw that the pKa of the carboxylate on glycine was 2.35. And the pKa of the amino group was 9.87. So let's break the molecule in half. Let's focus here on the carboxylate. So that was given, and that's given in the previous example. So we're going to compare the pH to the pKa. So here's your pH. pKa 7.4 is greater than 2.35. So when the pH is greater than the pKa, the predominant form is going to be the deprotonated form. All right, so we draw the oxygen with a negative charge. Let's do the other half of the molecule. Let's compare the pH and the pKa. So the pH was 7.4, the pKa was 9.87. When the pH is less than the pKa, the protonated form predominates. So the protonated form of the amine is NH3 with a positive charge. And that concludes this lecture.